Okay, in this video we'll be introducing partial derivatives. This concept will unlock a lot of the things that we're going to look at in multivariate calculus. This example up top of your notes gives a pretty good intuition about what partial derivatives tell us. So this reads, if you were running on a treadmill that is capable of moving at different speeds and at different slopes of the belt, and you are interested in measuring the calories burned, you would be able to put together a formula F. The function for calories burned is a function of two variables. Belt speed is a variable, and slope of the belt is a variable. In Calculus 1, you learned about derivatives, and you learned that the derivative is just a study of how one variable changes with respect to changes from another variable. When we have a multivariate function, your dependent variable depends on more than one independent variable. For example, we could study how calories burned changes with respect to just the belt speed. And one way to do that is we could keep the slope of the belt constant and then just change up the belt speed and measure the calories burned for different values of belt speed. Or if you want to see how the slope of the belt affects calories burned, you could keep the belt speed constant and then just change up the slope of the belt. So in the 2D world, we had different ways that we could denote a derivative. If your function was written as f of x, then we typically would just use f prime of x to show the derivative. If it was written as y, you could also use that prime, y prime, or you could write it as dy dx. When we're in the 3D world, there's also different ways that we can denote a partial derivative. If your function is written as a function of two variables, say f of xy, that would have two different partial derivatives. It'd have a partial derivative with respect to x, and you could write that as fx of xy, or there would be a partial derivative of f with respect to y, and you could write that as fy of xy. Instead of writing fx of xy every time, you could just write fx. And then instead of fy of xy, you could just write fy. There's also this notation here. That funny looking d is a lowercase delta. So this could read delta delta x of f of xy. So that lowercase delta symbol, typically you'll see people draw it like that. It's just a lowercase d that curls over at the top. So this is the delta symbol. And often you'll hear mathematicians just call that del for short. So if you're reading this to yourself or to someone else, you could say delta delta x of f of xy, or you could shorten it and say del del x of f of xy. So this one over here would be del del y of f of xy. To me, it's a lot easier to write, read, and to say fx or fx of xy and fy or fy of xy. So these are the notations you'll see me use most often for partial derivatives. So the other option was if you have a z to denote your multivariate function. So the partial derivative of z with respect to x could just be written as zx, or the partial derivative of z with respect to y could be written as zy. If you're going to use the delta symbol, then you could write it as del z del x or del z del y. When you first learned derivatives in Calc 1, you learned it first as a limit using the difference quotient. And that was actually the hard way to calculate a derivative, but it's important to know that method because that method uses the strict definition of a derivative. So we'll do the same here for multivariate calculus. The partial derivative of f with respect to x would be the limit as h goes to 0 of your difference quotient. And then since you're looking for the partial derivative of f with respect to x, you want to put x plus h where you had an x. So example 1, for f of xy is equal to x squared plus 2y, find fx and fy by using the definition. So then for fx, we're going to do the limit as h goes to 0, and then everywhere you see an x, replace it with x plus h. That would give us x plus h quantity squared plus 2y. Then we have to subtract out the original function, so we do minus x squared plus 2y. And then everything is divided by h. The goal here is to get rid of the h in the denominator. So we need to simplify the numerator by multiplying everything out and distributing the negative that was in front of that parentheses. And then notice the x squared up front will cancel with the negative x squared at the back, and the 2y in the middle there cancels with the negative 2y at the back. That would give us the limit as h goes to 0 of 2xh plus h squared over h. Now everything in this fraction has an h. So that h and one of the h's from the h squared can cancel with the h in the denominator. So our limit would reduce to the limit as h goes to 0 of 2x plus h. Now if we do direct substitution, we can just plug in 0 for the h, and we're left with 2x. And that is our partial derivative of f with respect to x. So go ahead and pause the video for a moment and figure out what the partial derivative of f with respect to y would be, using the definition of the derivative. Alright, so here's what I got for the partial derivative of f with respect to y. So then our answer here is just 2. The faster way to find a partial derivative is using all the rules that you learned in Calc 1 for finding the derivative. And as you calculate a partial derivative with respect to a specific variable, you want to treat all the other variables in the problem as a constant. So here's how that works. Let's say z is equal to x cubed plus x squared plus y cubed. And we want to find the partial derivative of z with respect to x. Instead of writing it as del z del x, I'm just going to write it as zx. So I want to go term by term in the problem, taking derivatives of just the x variables. Any other variable I see, I'm going to treat it as a constant. So this first term, x cubed, I would just take the derivative of x cubed with respect to x. That would be 3x squared. Now the next term, x squared y squared. I'm taking the derivative with respect to x, so the derivative of x squared would be 2x, and then that y squared, I just treat it as a constant. So it just gets copied down after the 2x. And then that third term, y cubed, there is no x in it. So y cubed is just treated as a constant, and the derivative of that would be 0. So then zx would be 3x squared plus 2x y squared. So now let's look at del z del y, which I'll just write as zy. This first term, x cubed, doesn't have a y in it. So the derivative of that with respect to y would just be 0. The derivative of y squared would be a plus 2y, and then that x squared just gets copied down. And then the third term, y cubed, the derivative of y cubed would be 3y squared. So that would be our answer. Zy would be 2x squared y plus 3y squared. Example 2. Z is equal to sine xy. We want to do zx, and we're going to have to use the chain rule for this one. Our outer function here is sine, and the inner function is xy. So to do chain rule, start by finding the derivative of the outer function. Derivative of sine is cosine. Keep what's inside the same, and then you want to multiply that with the derivative of what's inside. And keep in mind what we're taking the derivative with respect to. So the derivative of xy with respect to x would just be y. So zx would be cosine of xy times y. Likewise, zy would be the derivative of the outside function. Derivative of sine is cosine. What's inside stays the same. And then multiply that with the derivative of what's inside. The derivative of xy with respect to y would be x. Alright, go ahead and try example 3, example 4, and example 5 on your own. See if you can figure out the partial derivatives of z with respect to x and z with respect to y. And here are my answers for these. This is what I got for 3, for example 4, and for example 5.